Let me get the recording going. So it seems to me that we have like two more topics to go over. One is resources and energy, and the other is the atmosphere and atmospheric issues. Um, and so when I looked at the book, this takes up 5 chapters. So I've already asked you to read this chapter, which in your book I think was 14. And then I'm asking you to read the next chapter in the next couple of days and so forth. It looks to me like we have just barely enough time to go over everything before the exam, but just barely. And maybe a day of practice. We'll have to see how long these presentations take. So first of all, resources and energy kind of go together, because a resource is anything that people use, would be one way to think about resources. And it could be a natural resource, or it could be something that people have created, like this basketball here. I suppose that would be a resource, which of course is going to depend on the natural resources, like the sap from the rubber tree that was used to make it. So natural resources occur in a couple different forms, and some are renewable and some are non-renewable. And basically the way I think about these is, if it can be replaced in a human lifetime, then it's a renewable resource, if it's replaceable. So the rubber tree can be replaced in a human lifetime, which makes the rubber that we use for basketballs and the tires in our cars and other things, that makes that a renewable resource. However, if we're cutting down the trees faster than they're growing back, we can convert it to a non-renewable resource. So renewable are renewable as long as we're not using them too quickly, as long as they're replaced. Now, some things are always replaced, like sunlight. We can't use that faster than it arrives. So no matter what, that's going to be renewable. Some of these resources are used for objects that we use in our everyday lives, like basketballs. Others are used for energy to run our machinery, to give us electricity, and for transportation is another huge use of energy. And it's kind of amazing to me. I sat down at lunch today and I pulled up my news app, and I'm kind of scanning through the different headlines. And the perfect headline for merging what we just talked about, water pollution, with where we're headed, mineral resources, was one of the headlines today. In fact, it was at 2 o'clock, I think, Eastern time. So basically, that would have been what time here? That would have been 11 o'clock. It was just posted. So what's happening, there is a river in Tennessee that they want to mine along the banks of the river. And what they're mining for is sand and gravel, which are often deposited by rivers. So it's a great place to get the sand and gravel. However, they never got the permit to do that, and they just kind of went ahead and started setting up their mining operation anyway. And it turns out this river has the highest biodiversity of any river in the country. And they were warned that they needed the permit, and they just ignored it. And then other people wrote to the permitting agency and said, you need to take action on this, because if there's a flood, it's going to have these terrible consequences. And 2 weeks later, there was a flood. And there's photos of this mining site with all this sediment-laden water coming out into the river, which, remember, sediment is a natural thing, but it's considered a pollutant when we disturb it. And when it builds up in waterways, it can interfere with the turbidity, the clarity of the water. It can carry nutrients into the water and cause eutrophication. And in this case, in this river, they have these small shellfish well, actually, they might not be that small. They might be the size of your hand, that are mussels related to clams. They have two shells, and these mussels are filter feeders. And so they filter particles out of the water, and they're great for the environment because they remove a lot of the junk that's in the water. In their natural habitat, they're good. Um, and in the East Coast, they have a variety of these mussels, and their role in the natural ecosystem has been to maintain water quality. Mussel populations have dropped dramatically because initially people like to make buttons out of their shells. And so they would harvest mussels with a giant, basically imagine a giant rake to pull the mussels off the bottom of the riverbed. And then they would cut the shells into buttons. And this goes way back hundreds of years that they were doing this. But anyway, the sediment can damage the surviving mussels. And some of them are endangered species, found nowhere else. There's some endemic species. Think about what endemic means. I've been dropping vocabulary, hoping that it's making sense to you as kind of a review as we go. But I found it pretty amazing that here's this issue with mining, which is how we get mineral resources, totally overlapping with our water pollution unit that we just went through really fast. Normally, I'd get so excited I'd print it out and have you read the whole thing, but we got to move on. So I'll just give them that 5-minute description. So, resources and energy. Resources, anything we use. Resources can be renewable or non-renewable, and our focus for today is mineral resources that we get from mining out of the earth somehow. These are not things that we grow. In fact, I've seen a bumper sticker that's pretty popular in Nevada that says, if it's not grown, it has to be mined. So if you're not growing a material that you're using, or it didn't come from a living thing, then it had to be dug out of the ground. And where this chapter begins is with some major geology ideas. And so what I want to do is begin with some diagrams showing some of the major events of plate tectonics, which kind of feels like it could be a distraction from where we want to go. However, I have seen AP exams in the past where they have a series of questions about plate tectonics. So I think we should go there because I know that they've included it in the exam in the past. So if you would go to Teams, and you should find an assignment, something like plate boundaries, I believe is what it was called. Does that sound right? Yeah, right there, plate boundaries. And you're going to download some diagrams, and we're going to add some labels to the diagrams to show what's going on at the different boundaries between the plates. So just a little background. People used to think that the entire Earth was unchanging. And then every now and then there would be a catastrophe, like an earthquake or a flood or a hurricane. But basically, they figured that the continents were in the shape that they've always been in. And then there was a German scientist who noticed that if you cut the continents apart, you could put them together like giant puzzle pieces. And the best example of this is the way that Africa and South America fit together. And he didn't have very much evidence for it, but we eventually found the evidence that convinced geologists relatively quickly in the 60s that, yeah, the continents had not only been connected in the past, but they moved around. And not only that, the ocean floors move around. And therefore, we have this phrase of a plate. So a plate is a piece of Earth's crust that can move. And basically, we think it's carried by magma down in the mantle. The magma is circulating in convection currents, and that drags the plates along. And then all these geologic events occur at the boundaries between the plates. Some events occur in the middle of plates, but most of them where the action is really happening is in the boundaries between the plates. And so if we understand these boundaries, we're going to have a good handle on what we're talking about with plate tectonics. Okay? Yeah. Yeah. So what I'm going to do is I'm going to label some of these boundaries. We have 4 different ones, as you can see. And then we need to describe what's happening. So what I'm going to ask you guys to do is add these labels and descriptions. I think it might be best if we created another document for the descriptions. So open up another document that will allow you to write down descriptions of what's happening at these boundaries. And this is going to be our first one. And hopefully you can tell that that's the ocean floor, with the water above it. And what I would like you to do first of all is add these labels.
Do we add them on the Word document?
What I would like you to do is add the labels to your diagram, and then we'll write out the descriptions of what they show in the separate document. So add the letters and the arrows. That's the way to go. That's pretty handy that you've got that right there, Ashley. Dang. Okay, so this is called a diverging boundary. And I don't know how familiar you are with plate tectonics, but let's just back up to these English terms of diverge and converge. At the beginning of class, we all come together into this classroom, so we have converged here. When things come together, they converge. And when the bell rings at the end of class, we'll all go our separate ways. We will diverge. So these are diverging boundaries, and you can tell by the arrows that I added on there that they're moving apart. Right? And this is happening at the sea floor pretty much all around the world. The most common example is what we call the mid-Atlantic ridge, right down the middle of the Atlantic Ocean. But it's also happening on some continents where the continents are getting split in half. And we think a new ocean will open up there eventually. And studying the sea floor is where we came up with some of the evidence that supports plate tectonics, as you'll see from some of these letters. So are you ready for me to start describing what's going on?
Give me 1 second.
Basically, people thought until we invented sonar that the ocean floor was pretty flat and there were no features on the ocean floor. Everything was the same. And then I'm not sure when they invented sonar, but in the last half of the 20th century for sure, they invented sonar, and that is basically when you send a sound straight down from a ship and you measure the time that it takes the echo to get back. The faster the echo returns, the shallower the water. that make sense? It's called sonar. Um, and when they did that, they discovered that there are underwater mountain ranges, like this one that goes down the middle of the Atlantic Ocean, from Iceland all the way down to Antarctica, basically. And it follows the same shape as the edges of South America and Africa. It has that same shape. And so here's what we found when we started studying that. Letter A, when they took a core sample of these rocks and measured the age, A was old rocks. But B, at the top of the mid-ocean ridge, was young rocks. Now, I didn't do it here. I'll do it here, but you guys don't have to add it to yours because it just starts to get too cluttered. But right here, we still have young rocks, and out here, we still have old rocks. So the rocks are very young at the top of the mid-ocean ridge, and the further away you go, the older they get, and the ages are mirror images of one another on either side. Like, just for example, if this was 1 million, 2 million, 3 million, 4 million close together, 5 million, see how I'm kind of making a pattern here? If those were the ages, we'd have that same exact pattern over here. Does that make sense? As if right here where 3, 4, and 5 are, a whole lot of rock was formed at the same time. Actually, that's backwards. This is where it was formed slowly. But whatever the pattern is on one side of the ridge, it's the same pattern on the other side. Now, not only that, for letters E and F, this is the buildup of sediments on the rock. And hopefully you can tell that letter E is a thin layer of sediments, and letter F is a thick layer of sediments. And once again, that's the same on both sides of the ridge. I just tried to simplify the drawing by not labeling all of them. And you don't need to either. E is thin sediment layer, F is thick sediment layer. Now the sediments take time to build up on the bottom of the ocean floor. So does that fit right in with the ages of the rocks that we measured? The youngest ones are close to the ridge, huh? Letter D is the mid-ocean ridge itself, this underwater mountain range. If I was to draw this in 3 dimensions, it would be something like this. Does that make sense? It's an underwater mountain range reaching off into the distance. Okay? And at the top of that mountain range, the mid-ocean ridge, letter C, you see there's like a valley at the top of the mountain range. And that's called a rift valley. And that word rift means it's being torn apart. It's spreading apart. So this whole piece of ocean floor is moving to the left, and this whole piece of ocean floor, moving to the right, and this whole piece is moving to the left. G is rising magma. And I think that takes care of all the letters, right? So what's going on is we have hot magma rising up here. When it gets to the top of the crust, it can't go any further, can it? So it spreads out to either side, and as it spreads out, it drags the crust along with it. But that means that we get this gap at the top of this mountain range, huh? And the gap fills in with new magma, which hardens into rock. So we have the rising magma actually lifts up the crust and makes the mountain range. Then it drags it off to the sides, splits it apart to make this rift valley, and we have brand new rock forming inside this rift valley as the lava reaches the surface and cools and hardens. In some places, this breaks through above the ocean. Like in Iceland, we get this very thing. So why don't you write down examples include Iceland and the Mid-Atlantic Ridge. There's a place in Iceland that you can basically go stand on this ridge line. So let's see, I'm going to bring this all the way up to here. Here's the island of Iceland, right? Where it broke through. And you can stand right here, and you're standing on Europe, and you walk across this little valley, and now you're standing on North America. I need to do that sometime. So you're right on this Rift Valley. There's another one of these. This Rift Valley is forming in Africa. And we think that the Horn of Africa is going to get torn off and a new ocean is going to open up. We think the Red Sea is the same thing that has happened, where a new ocean has split Arabia away from Africa. Okay? Are we good with diverging boundary? So diverging moves apart, it makes new crust. What's the next one? Let's do that one next. This is the most complicated one, so let's do it last. Let's do, oops. This one, huh? Right, this one? Does yours look like that? Has those stars and squiggles on it? Good. So there's our labels. Along with a title. So converging means they do what? If they converge, they move together, move apart, or slide past each other. They move together. So I'm going to add arrows showing that these continents are crashing into each other. Down here in the mantle, the magma is being brought together and then cooling off and sinking down. And that motion is what's actually bringing these two continents together. Okay, so you can see that letters A, B, C, and D are all layers of the Earth. So letter A is called the lithosphere. And you can see that it has two parts. Letter B is the crust. So this is all solid rock up here. This is all granite. That's the crust, letter B. Letter C is the upper mantle. But because the crust and the solid crust and the liquid upper mantle move together, they act like they're one thing, and that's why we call them, as a pair, they're the lithosphere.
Okay, so the lines are the lithosphere?
No. A is the lithosphere.
Oh, dang it.
B is the crust. And I just colored in what the crust would be,
Okay.
right? Because you already learned that the Earth is crust, mantle, and core, right? But there's a little more complication than that. The mantle is divided into an upper part, which is letter C, the upper mantle, and a lower part, the lower mantle. which also has this other name that I don't think we need to worry about. It's the asthenosphere. But the lithosphere is the crust combined with the upper mantle because they move together. As one moves, the other moves. Basically, the movement of the magma in letter C, the upper mantle, drags the crust along with it. And in this case, two continents got dragged together. So letter E is continental crust. And I think what I'm going to do is I'm just going to make this be a letter E also, because they're both continental crust here. So just change that I to an E.
E is continental.
E is continental crust. There's two different kinds of crust. There's the crust that forms the ocean floors, oceanic crust, and then there's the crust that we walk around on all the time, the continental crust. Now, just imagine, these things are moving in slow motion towards each other. The speed would be, they say it's about as fast as your fingernails grow. That's how fast the continents are moving. So in this case, they're pressing against each other harder and harder, aren't they? And where are they going to go? They're going to crumple up, and they form these mountains. And the rock is very damaged here. It's compressed and squeezed and folded and fractured. But what I'd like you to label for letter F is folded mountain range. And letter G, folded rocks. Some of the rocks actually get folded. This became kind of a joke in my earth science class one year until I brought a couple of samples to show them that, yes, you can fold a rock. Look at those layers. Can't you see those are folded? Yeah? And then look at this one. This got squeezed like this, didn't it? See that? Folded rocks from the high pressures. So here's a folded rock. You can see the layers where it got squeezed there. And here's another one showing you some folds in these layers. And we can see these on a huge scale too, in whole layers of mountainsides. Letter H, well, just imagine if these are pressing against each other, aren't we going to have earthquakes now and then? So letter H represents earthquakes. And then I'd like you to write down an example, which would be the Himalayas, Himalaya mountains. The tallest mountains in the world are these folded mountains as a result of India colliding with Asia. India moved north from where it used to be and hit the southern edge of Asia and is still pressing Asia further and further. And the Himalayas are growing taller and taller. And maybe 5 years ago, there was a huge earthquake in Nepal. I don't know if you heard about that or not, but it was very harmful. And that's our first converging boundary. We actually have another one that we'll talk about in a moment. But first, let's do this one. Now, this particular plate boundary could be any kind of plate. And they're not colliding, and they're not spreading apart. They're moving from side to side. So we call it a transform boundary. And in this case, it looks to me like this plate is moving in this direction, and this plate is moving towards us. See how it's kind of a three-dimensional drawing this time? To make that a little more obvious. And I guess we'll just call A and D, we'll call them plate 1 and plate 2. They could be continental crust, or they could be oceanic crust. It can occur either at the ocean floor or in the middle of a continent. And the line where they meet is labeled letter B here. I don't know if you can tell from that arrow. It's pointing at the line between them. That would be a fault. And I've used the same symbol for earthquakes as I did on the previous diagram. That's letter C. Those stars are earthquakes. And then the last thing on this one is an example, and our best example is the San Andreas Fault.
So you're gonna have to send me that. What's A?
It's just plate number 1, and D is plate number 2.
Okay.
B is a fault, C is an earthquake. So as these things are grinding past each other, they get stuck, and the pressure builds and builds and builds until the force overcomes where they're stuck, and suddenly they slide, and that's what we experience as an earthquake. So in 1906, there was a huge earthquake in San Francisco, and really almost destroyed the city, although it wasn't the earthquake that destroyed it so much as it was the fires that started because of the earthquake. All the water lines got broken, so they couldn't put the fires out, and they burned for like 3 days. And there's a place that you can go today, a national park north of San Francisco, where they have, they think it was close to the epicenter of the earthquake, and there's an old fence. And so the fence would have been, going across the ground to keep the animals in or out or whatever. And the earthquake broke the fence and carried one part one direction, the other part the other direction, about 20 or 25 feet. And this would have all happened within about a minute and a half, like the length of this room, that much motion on the ground surface. So it must have been spectacular. Hopefully you weren't in the middle of the falling rubble or something like that, right? One of my favorite pictures is there was a statue of a guy up on top of a building, and the earthquake knocked it off the building, and it fell like a spear and stuck his head into the pavement. So he's sticking up out of the ground like a giant lawn dart. Hopefully you didn't get hit by the guy, though.
You just call.
And then the last one. There you go. This one is called converging number 2. Converging boundaries 2.
I hate this. Where are they?
Sounds like you're having some technical issues.
Yes.
Sorry. I am recording this though. And this one has like a subtitle of a process that occurs here called subduction. So if it's converging, what direction should I draw the arrows? Converging means they come together, right? I see. So these are all kind of in random order. I think because this was probably drawn as a test question. But I want to present them in a more logical order. So we're going to jump around with the letters a little bit. So maybe you should set up your notes so that it says A through H, and then we'll jump around from one letter to another.
A through H.
Yeah. Actually, make that A through I. We're going to add one more at the end.
So A, B, C, D, G, A, F.
Okay. And I think we'll just start with letter H because that's just to help us get oriented to what's going on. That's the ocean. Does that make sense? That's the ocean there. Which means letter F would be what kind of crust? What about letter G? What kind of crust would that be? It's really thick.
Oh.
You could walk around on here. Here you'd have to be in a submarine, huh? Because G is continental crust, and the way we refer to the bottom of the ocean floor is that it is oceanic crust. So letter F, oceanic crust, and letter G, continental crust. Now, can you see that when these two come together, that the ocean floor gets pushed underneath the continent? When they come together, I like doing it this way. Here's the continent, here's the ocean floor, and they collide, and the continent goes over the top of the ocean floor. The reason is they're made of different kinds of rock, and the rock that makes up the ocean floor is denser, so it sinks a little easier. And this process that I just described is subduction, where where ocean crust is pushed underneath continental crust. So letter D is called the subduction zone. This is where subduction happens. And I think you should include that brief description. Subduction zone, where ocean crust is pushed underneath the continent. Now, as the ocean crust is pushed underneath, notice letter E. Can you see that this part of the ocean kind of got pulled down even deeper? See how deep the water would be right here? It would be this deep, but here the water would be that deep, wouldn't it? Right? It's a much deeper place in the ocean. In fact, these are the deepest places in the ocean, and we call them deep sea trenches. So letter E is a deep sea trench. The deepest one in the world, if you've heard of it, maybe not, is called the Marianas Trench. And it is 7 miles deep. And just to put that in perspective, Mount Everest is 5 miles high. So you could drop Mount Everest into the Marianas Trench, and there would still be 2 miles of water on top of it. Right? It's really deep, 7 miles deep. Okay, so that's the deep sea trench. Now, think about this. As this ocean floor is getting pushed underneath the continent, what's happening to its temperature? The rock of the ocean floor is getting pushed down into the mantle, isn't it? What's happening to the temperature of it? As we go deeper into underground, it gets hotter, right? Yeah. So what's going on with letter C? It's
burning.
It's melting.
It's melting.
Yeah, so letter C is showing the ocean crust is melting, which makes magma. And if you don't know the difference between magma and lava, the only difference is whether they're underground or on the surface. So we call it magma until it has erupted, and then we call it lava. So we have this magma that's formed, but magma is very hot and low density. So what does the magma tend to do? It tends to push its way up through the continent. So this is rising magma, letter B. Rising magma. Magma's rising upward.
Wait.
Oh, I guess we didn't need an I because I've got A. I just didn't draw it. What's going to happen when this magma reaches the surface?
It explodes.
Yeah, sometimes it explodes, sometimes it just flows out. But one way or another, what are we going to have? We're going to have a volcano.
Yeah.
And of course, as the magma is pushing its way through the surface, there's also earthquakes. There's also earthquakes along letter D, along the subduction zone. So letter A, I didn't draw the volcano on here because like I said, this was, I think this diagram was intended to be used as a test and I didn't want to give away what it was too much. So letter A should be a volcano erupting right there.
Like volcano.
Nice. Yep, that's perfect. So that is like, what did we just do?
Wait, A is a volcano erupting.
Yeah, A is a erupting volcano. So you can see that plate tectonics explains a lot of things that are happening in the Earth. It explains volcanoes and earthquakes. It explains the formation of mountains. And for our purposes, one of the most important things that it also explains is why we get deposits of gold and other minerals in certain locations. That's all going to be related to the movement of these plates. Why do we get gold where we do, or diamonds where we do, or iron where we do? And so that leads us right into the study of these mineral resources. Okay? Oh, wait a minute. One more thing. Example for this one. There's a lot of them actually. Japan. All the Japanese islands were formed like this. I don't know if you've heard of Mount St. Helens in Washington State. It erupted in 1980. So it's pretty famous because it was on US soil. Those are a couple good examples. The Philippines, Indonesia, these are all examples of where subduction is happening. The Andes Mountains in Peru and Chile are formed through subduction also. All right, so let's go ahead and dive into the PowerPoint. I encourage you to take notes on this if you like.
Take notes.
There we go.
Where's the notes?
Okay, I'm just going to remind you 3 main layers of the Earth. You guys know those? Crust, mantle, core? Yeah. Had that since what, 3rd grade? Yeah. Okay. Now here's a diagram that combines everything that we just looked at. Can you see where subduction is happening? Where the ocean floor is getting pushed underneath a continent. Do you see where subduction is happening? Right here. And does it show magma rising to make these mountains? Can we see oceanic mid-ocean ridge here, where we have a diverging boundary taking these plates apart, right? Here's a diagram of what we think is going on deep in the mantle. These yellow arrows are showing what we consider the convection currents, where the hot magma rises and spreads out. And as it cools off, then it sinks again. And we end up with these big loops, these big cells, convection cells. I think you're in the wrong one.
Is it not?
It is not that way. It is chapter, it should be non-mineral, non-renewable minerals. It should be the first one of the 3.
Non-renewable.
Resources and energy.
Okay.
That's the one. And I'm moving on. Okay, so then we have these plates, the crust that gets carried along with these convection cells. And here's a nice map showing the plate boundaries. It shows the major plates. There's maybe 8 of them. And then there are several minor plates, smaller plates as well. And remember I said that most of the geologic activity occurs in these, on the edges of these plates, right? So can you see where the San Andreas Fault would be along the boundary of California?
Yes.
And you can see going right down the middle of the Atlantic Ocean, we have this mid-Atlantic ridge that I was talking about. And again, doesn't it follow the shape of South America and Africa? They all three have that same shape, that bend in the same place. The Marianas Trench, the deepest spot in the world, is over here on the edge of the Philippine Plate. But I want to ask you something. If most of the geologic activity is happening on the edges of plates, please have a look at Hawaii. You guys know where Hawaii is on this map? It's basically about here. Is it on the edge of a plate or in the middle of a plate? Yeah, so Hawaii is a unique example of another thing that happens, which is called a hotspot. In some places on the Earth, there are specific locations where magma is rising. And so that's why they call it a hotspot. As the magma reaches the surface, we get volcanic activity, right? And if you think about Hawaii, it's a chain of islands. And note, if you think about the map of Hawaii, they don't make a circle. Instead, they're in a line. It's not a perfect line, but like if my fingers were each an island, that could be the Hawaiian Islands, right? And what we think happened is this. Magma came up and made this island. And then the plate dragged that island away from the hot spot. The magma came up and made a second island. The plate moved and dragged both of those islands further away, which allowed a third island to grow, a fourth island, a fifth, a sixth, a seventh, a 10th, a 20th, a 50th. Well, wait a minute, Hawaii doesn't have 50 islands, does it? But now that we've mapped the bottom of the ocean, we've found like 50 islands in a line, most of which the top has eroded away, so they're below the waves, the older ones. Not only do we have this line of islands, but if we measure the ages of the rocks, if the hot spot is where my little finger is, those are the youngest rocks. These are a little older. These are older. These are older. These are the oldest. So it fits in with our explanation. Even though it's not at the boundary, this hot spot activity is still explained by plate tectonics. And here's nicer diagrams than the ones that we just drew, but they're the same thing. You see the divergent one moving apart? Convergent coming together. This one's showing subduction. And this one, it's a little harder to tell the way they did it. Their transform boundary is back in the background here. Ours was more this way, right? So. Here's a photo of the San Andreas Fault, which is a transform boundary. And it's hard to tell, but there is a place where a creek crosses the fault, but the creek bed is broken by the fault. And so the creek used to come across the fault all in one piece, but now it's been split. Okay, enough of plate tectonics. Another important process for us is weathering and erosion. So whereas plate tectonics tends to build geologic features, weathering and erosion tend to break them apart. And of course, all of these things have influences on ecosystems. If nothing else, it influences the type of soil that you find there. The difference between weathering and erosion, weathering breaks things apart, and erosion moves the particles to a new location. So if I take a hammer to a rock and pound it into bits, that was weathering. If I then sweep those particles to a new place, that was erosion. There's actually a third process involved, which is when those particles get dropped off, and that's called deposition. They get deposited. And that's the one that can be a problem for like the mussels that we were talking about earlier. So the mine along the edge of the river was causing weathering, breaking materials apart. The river then carried them away in the process of erosion. And when the river dropped them off and buried the mussels, that was deposition. Okay, let's talk about a mineral versus a rock. A mineral is a pure material. A rock is a mixture. So a mineral is pure. It has a chemical formula. That's what I mean by it being pure. A rock is a mixture of minerals. A rock, let's see, I like comparing these things to a salad. A rock is the salad. The minerals are the ingredients of the salad. The lettuce and the tomatoes and the carrots and the croutons and whatever you put in your salad, those are the minerals, the pure things. When you mix them together to get the salad, that's when you get the rock. And around here, our most well-known rock is a great example of this. Granite. You know the way granite is kind of speckled? It has white and black spots in it? Those are the different minerals that make up the granite. There are 4 different minerals found in granite, which you don't need to know, but they are quartz, hornblende, feldspar, and what's the 4th one? Quartz, feldspar, hornblende, and mica. Mica is the one that the kids like down on the beach. And you probably did this too when you were little. Did you ever go to the beach and you're looking in the water and you see these little golden flashes in the water? You can see it now too. You don't have to be a kid to see it. But the kids are like, oh, look, it's gold, right? And then you pick it up and there isn't any. It's because it's actually black. It's a black mineral, but it's very flat and it reflects the sunlight, so it looks golden. Yeah, you got played. So a mineral is pure, a rock is a mixture. Now, have you heard of an ore before? Have you ever heard this word ore, like iron ore?
Yes.
O-R-E. Okay, let's write down what that is. An ore is something that we mine for. It's the unpurified material that we would mine for. That's the ore. And the ore could be either a rock or a mineral. And then often you have to purify the ore to get the metal, for example, that you wanted, to get the aluminum out of it.
Is this folded?
Okay, so mineral resources are basically the ores that we're talking about here, the things that we dig up. And it could be as simple as sand. We have a huge need for sand for construction, for roads, etc. Or it could be as fancy as an ore of gold that we dig out of the ground and then purify to get the gold. And we can classify these mineral resources into 4 types. The ones we know about are identified. The ones that I don't like the order that they presented this in, but the ones that we not only know about, but we know we can dig up profitably, if we can make a profit, we call those reserves. Mineral reserves mean we know about them and it would be profitable to dig them up. Undiscovered mineral resources are ones that we assume are there, but we don't know exactly where. We'd have to do some more studies to be able to identify them more precisely. So here's the way to look at it. This whole box is showing all of the mineral that we're talking about here. It could be a fossil fuel, it could be an ore of copper, or it could be a supply of sand. So the entire box is that mineral. In this case, it's divided 50-50, but that's not necessarily so. The identified ones are on the right. Of the ones that are profitable, we call those the reserves. Does that make sense, what that diagram is showing there? Yeah. So this whole box is all those minerals that exist, all that entire resource. But some of them, we don't know exactly where they are, the undiscovered ones. But we think they're there, but we don't know exactly where. These ones, we pretty much know where they are, the identified ones. But they're not always profitable to dig up. Those ones, maybe they're too spread out. We know where they are, but they're not concentrated enough. It would be way too expensive because you'd have to dig such a giant mine to get just a little bit of the gold out, for instance. And that changes over time. What is economical or what is not economical depends on your technology. So when they were digging gold and silver in Virginia City 150 years ago, they were doing it all by hand, right? And now we have these machines that can do it. And we can now profitably mine for microscopic gold. So they take huge amounts of earth out of the ground and they grind it up and they treat it chemically that removes the gold from it. And this is hundreds of tons to get a couple ounces of gold. But because we have the machinery that we have, it's efficient enough that they make a profit from it. So that would now be a reserve. Whereas back in the old days of Virginia City, it might have been identified, but you couldn't make any money doing that because it would all have been done by hand. You guys remember the three types of rocks? I like to say, do you guys know the three rock groups? The Beatles, Pink Floyd, and Led Zeppelin? Sedimentary rock, metamorphic rock, igneous rock. Sedimentary rock, made from sediments. Might be made from sand, might be made from gravel, might be made from clay, might be made from mud. That's compressed together and cemented together. Igneous rock comes from lava or magma. It comes from the word ignite, to burn, igneous rock. So it was once very hot. And metamorphic rock has been changed. So it might have started as a sedimentary rock, and then it was changed by heat and pressure. It could have also started as an igneous rock, but been changed by heat and pressure. And these three different kinds of rocks can be converted into one another following what we call the rock cycle. So you can start anywhere on this diagram, really, but let's start with the volcano. So this volcano erupts and it forms some igneous rock like granite. And over time, weathering breaks the granite down into little bits of sand. Erosion carries those bits of sand to the ocean, and drops them off, deposits them in the ocean, and they build up more and more and more, where heat and pressure compress them into sedimentary rock, like sandstone. And then eventually, that sandstone, by plate tectonics, could get pushed deeper underground, where it gets changed into a metamorphic rock. If it gets pushed far enough underground, it completely melts to make magma, and we've completed the circle, huh? You could also have some shortcuts where the metamorphic rock doesn't melt completely, it gets pushed to the surface and picks up on the weathering step. Or where the igneous rock gets pushed back underground right away and gets metamorphosed, gets changed. So we think that all the rocks are actually interconnected with one another, and one rock type is converted into another frequently. And we just want to mine for the things we need at the correct part of the rock cycle. But mining has some environmental impacts that we need to talk about. First of all, there's a bunch of steps involved. Here we are mining at the surface. In other words, we're digging a big hole on the ground, as opposed to tunneling underground in a mine shaft. That would be underground mining. Either way, we're trying to get this ore. That's the raw material we dig out of the ground. And then we have to separate the good ore from the waste rock, which they call the gangue. Then you take your ore and you have to smelt it to separate the mineral that you want from the rest of the rock. And you can see this often happens in factories, which can pollute the air and the water by releasing waste chemicals in the process. Then we melt the metal and we form it into whatever shape we want, right? And then we can either throw it away or we can recycle it. And if we recycle, we can avoid these first three steps, can't we? We can skip mining. So it turns out that one of the main sources of aluminum is in Brazil, which means if you recycle your cans, you are helping preserve the rainforest. Because if you don't recycle your cans, they have to cut down more rainforest to dig up fresh ore. So this diagram is showing the steps in the process of getting the non-renewable mineral resource. We have to get it first, we have to process it second, and then we get to use it eventually. Along the way, we have a few other steps. We have to explore for it, we have to remove it, we have to find it. We've got to convert it into what we want it to be. We have to then transport it to the people, manufacture what we want. Then we get to use it for whatever, and then it gets discarded at the end. And each of these steps can have different negative environmental impacts. Which is crazy to think, okay, how did the molecules in this key get to me? Where were they before they were in my pocket? And where are they going to go in the future? And that's just a little thing like a key. This is comparing the two main types of mining, either mining on the surface above ground or underground with subsurface mining. Now, what do you think? Is this surface mining or subsurface mining? We don't have guys going down a little mine shaft there, do we? We just have a giant hole in the ground. So this is surface mining. And when it's this big, they call it an open pit mine. And please notice that each of these kind of layers on the hill is wide enough for a truck to drive along it. So that's how big this pit is. A lot of times these pits are dug deep enough that they go below the water table, which means they're constantly filling up with water, and they have to pump that water out of there. And here it says toxic groundwater can accumulate. Well, why is it toxic? Because a lot of this rock that we're exposing has not been exposed to the air or to water for maybe millions of years. And so we have chemical reactions that occur with the water and the fresh rock that make it toxic. We think one of the biggest mines in Nevada is going to be an open pit bigger than Lake Tahoe, so big that when they're done, it would be too expensive to fill it in. So they're just going to leave this big hole in the ground, and it will fill in with water, but it'll probably not be a good ecosystem and might even be toxic. This is the remnants of strip mining, where you dig up a layer of the Earth's surface, and then you move on to the next strip, one layer after another. And after you're done, you end up having these piles of material, basically the rock that has been pulverized. This is all the leftovers from the mine. And you might remember that when we studied solid waste, that industrial solid waste was much more of a problem than garbage from cities. And that's because of things like this. This is hundreds and hundreds of tons. You can see how big the roads are in the background. Hundreds and hundreds of tons of pulverized rock. It's not soil, because it's just rock. It doesn't have any of the organic components in it that we would need for it to be soil. Here's a diagram showing how this strip mining happens, and some good vocabularies on here too. And in this case, they're showing a coal mine. So in this coal surface mine, coal is also mined underground in mine shafts and stuff. But in this case, there's a whole layer of coal in the ground here. And so the first thing they have to do is dig down from the surface, right? Along the way, they found another coal seam. And any of the rock that's not wanted, that's above the coal, is called the overburden. And that's just rock that's in the way. And in this case, that overburden just gets dug up and moved over to the spoil banks. And it just basically becomes waste rock that doesn't really support ecosystems very effectively unless you cover it with a nice thick layer of soil and contour it so that the water flows naturally. So some mines are good at reclaiming the landscape after they've dug it up, and others are not. Here's another type of mining for coal, generally, that occurs in parts of the eastern U.S. It's called mountaintop removal mining, which is just what it sounds like. You're basically taking the top of the mountain and you're pushing it downhill, which can block off the flow of a river in the process. And that gives you access to the coal that was underneath the mountaintop. But it can also interfere with the ecology of the aquatic ecosystem, not to mention the forest that was on top of the mountain before you removed it. In addition to all this, we have another water pollution problem that happens here, and that is the rainwater that flows through the disturbed rock and through a mine often dissolves acids and carries that acid down to the stream downhill from it, or lake, or whatever. So they call this acid mine drainage. If a mine has acidic water coming out of it. So once again, we're seeing where mining and water pollution are kind of connected here. So some of the impacts besides disturbing the landscape just directly by removing the overburden is that we have to smelt and treat these ores to extract the desired metal. And sometimes these metals are toxic. So it turns out that a great way to remove gold from its ore is by using mercury. And we should have picked up that mercury is a toxic metal, right? One of our water pollutants. It also comes from burning coal, but and it causes brain damage and all kinds of nasty things. It can be toxic in high enough levels. So in the Virginia City days, what they would do is, and this often is still happening in developing countries where they're mining for gold, is you crush up the ore. You have some way of pounding the rocks until it crushes into as much of a powder as you can get. And then you run that crushed ore through mercury, and the mercury binds to the gold. It basically pulls the gold out of your crushed rock. And then you let your crushed rock sink and you gather all your mercury, and if you heat that up, it will remove the gold from it. Well, in the meantime, you're breathing those mercury vapors. And then you have some leftover mercury at the end that here at Virginia City, they dumped that waste mercury into the nearby river, the Carson River. And this is why the Carson River is one of the Superfund cleanup sites. Remember, the Superfund is it's a bank account to help clean up toxic sites. And the Carson River is one of them because of the mercury from 150 years ago when they were mining for gold. Today, they don't use mercury so much. Instead, they use cyanide, which, if you know anything about cyanide, it's also toxic. And we'll see how that works. I've got some diagrams here. All right, so if we think about supply and demand, if people want gold and it becomes more and more expensive, does that encourage us to be more efficient about the way we use it in a way? So that's something to think about. Just how supply and demand can influence our environmental impacts. Okay, these are called depletion curves. When we see these three different curves, time is across the bottom. Can you tell that you would run out of your resource, whatever it was, if you followed curve A? You would run out of it faster than if you followed curve C. This is time across the bottom. A, you use it really fast. You dig it up, you throw it away, and you run out of it. C, you dig it up, but you also recycle it and reuse it. So you don't need to dig it up quite so fast, do you? And so you can expand the time that you have to use it on these depletion curves. Basically, we're talking about adding efficiency into the equation of our use of resources. And we make them more and more close to being renewable if we're more efficient about it. This is kind of what I was talking about before with how gold in the past, you'd have to be able to dig it out by hand, but now we can dig up microscopic gold and it's still profitable because of our new technology. We might be able to mine from the oceans as well. I don't think the technology has been developed yet. But this is an interesting ecosystem here. In some spots on the ocean floor, we have underwater hot springs. And they often call them black smokers or white smokers, depending on what the water looks like as it's coming out of that hot spring. And they often contain sulfide. And it turns out there are some bacteria that can get energy from sulfides. Even though this is a couple miles deep and completely dark, so there's no photosynthesis, bacteria can get energy through chemosynthesis. And that starts this whole ecosystem of these other creatures. These tube worms are like 6 feet long. And they have these red things look kind of like feathers. Those are their gills. And they are using them to filter bacteria out of the water to get their food. They're also doing gas exchange with the water. So it's like an underwater desert along the bottom until you get to one of these hydrothermal vents, one of these underwater hot springs ecosystems. But that means there could also be some good minerals right there that we could mine for, huh? But that might have a negative impact on this unique ecosystem, which is totally independent from the sun. Recycling metals saves money, has a lower environmental impact than mining and extracting them from an ore. So how can we use our minerals more sustainably? Here's a whole list, right? I'm not going to read through the whole list. You can do that on your own. I'm going to get past this. So if we look at this diagram, what they're suggesting here is we create not individual industries, but ecosystems of interconnected industries, where the waste from one industry is used by another industry. So we talked about thermal pollution from a power plant, the waste heat from the power plant, right? Well, we can use it in a variety of ways. The sludge from fish farming, the waste from the fish basically, could be used as fertilizers by the farmers, and so on. So we're connecting. This is one possible solution to a lot of environmental problems at once, is to interconnect these different industries. Oh, that was the end. Okay. Okay, we only have 5 minutes, huh? So let's look at the end of our last class, we drew this diagram. This is a little better version of it. Does it look familiar to you? Okay. So what's going on? Let's review. What's number 1 represent?
Can I take mine? Oh, it's.
Let's see what we can do just from our
Okay.
brains. We only have 5 minutes, so let's just see what we can do from as a review.
It's burning.
It's the fuel that's burning.
Yeah.
In this case, it's supposed to be coal, but it could also be oil. It could be natural gas. It could be wood. It could be garbage. Number 2, the device that we burn it in is called.
No.
Oh, that's number 3. A furnace.
The furnace.
Whatever you burn it in, that's the furnace. And we're burning it because we want to do what?
Steam.
Yeah, we want to make steam. So this is the boiler. So we're boiling water, or it might be some other liquid. So we want to make this steam. Are there other ways to heat up the water without burning something? One way is nuclear power. the nuclear reaction, the chain reaction, releases heat, and we can harvest that heat to boil water, and we don't have to burn anything. But we do need uranium, we do need a radioactive metal to be able to give us that heat. We can also use solar power to heat up water in different ways, and we'll look at some of those ways later. So we make this steam, and we get it into high pressure by squeezing it, huh? And the high pressure steam is going to do what? What is number 5? Spinning around.
Turbine.
It's turning the turbine, right? And again, we could get rid of all 1 through 4 if we just had a wind turbine, or if we had something that moved with the ocean, with the waves, could possibly get things moving for us. Once we have that turbine turning, though, then we send it to we use the turbine to turn this axle inside of this is where we actually make the electricity, inside the generator, because it generates, it creates electricity. And the way it does this, number 7, is by having a turning coil of wires inside of a magnetic field. And that gets the electrons moving. Once the electrons are moving, we call it electricity. It gets carried out on the power lines, and it goes to home and businesses where Homer can sit there watching NBC.
Yes.
Right? Okay. So please read the book, you guys. What do we have? Today is the 5th. And then that means we have 22 days till the big exam. Yeah. And after that, I'm going to try to do a bunch of labs and maybe a little mini field trip or 2.
Yeah, please.
Yeah, and we'll be done taking notes. I will probably have to give you a test here or there, but right now I just want information in, right?
Yeah.
And then you can give it out on the big exam day, okay? So.
Are we gonna have a final too?
Yeah, we'll have a final. Yeah. That'll be during finals week in mid-June, right? So we've got like 6 weeks till that. Your results from your AP exam will be available usually around the 4th of July. Although because we're doing the later test, it might be a little later than that, I'm not sure. Okay, thanks. That's all I have for you today.